Second in this session is Lilianne Nakazono, which is a PhD student at the University of Sao Paulo.
Hi, everyone. I'm Lilianne. I'm from University of Sao Paulo, and I'd like to, first of all, thank the organizers, okay? I will try to answer this question, how narrowband surveys can provide a better quasar selection. And for that, I'm going to show you some analysis that we have made based on S-PLUS data, and S-PLUS is a narrowband photometric survey. So in that sense, let me first introduce S-PLUS to you. So S-PLUS stands for Southern Photometric Local Universe Survey. And although there's this local universe in the name, we are trying to find quasars in these observations, and this is one of my main goals for my thesis. And S-PLUS is observing the southern hemisphere. It will cover more than 9,000 square degrees with an 86-centimeter telescope. And this telescope is located in CTIO in Chile. So you'll see in this picture here, this is our dome. And this is an example of an S-PLUS field. This image is from the region of the Hydra cluster. So you see the whole field here of 1.4 per 1.4 square degrees. You have a zooming in the right panels where I show you a view of 15 arcminutes, a view of 2 arcminutes, and a view of 12 arcseconds. And this map will show our coverage and other surveys coverage just for comparison. So all these red regions in this map will be covered by S-PLUS. And I don't know if you can see very well here, but all this field tiles are the tiles that were already observed by S-PLUS, at least at the moment of the publication of this paper. So of course, right now we have more tiles observed than that. And the uniqueness of S-PLUS is its filter system, which consists of narrowbands and broadbands. Here you can see the efficiency for all 12 bands, in which 5 of them are broadbands, similar to slow ones, except for the U-band, but GRIZ or SDSS-like. And 7 narrowbands that, as I show here, are centered in some important features like H-alpha. And here I show you the photometric depth and coverage area of S-PLUS and how it compares with other surveys. The shape size here scales with the number of filters, okay? And for the narrow bands, the photometric depth, it's typically 20.5 magnitude, except for H-alpha that is 21 magnitudes. It's above 21 magnitudes. And for broadbands, it's typically 21.5, except for Z-band, that is 20.6 magnitudes. Here I show you some spectra from Sloan for a quasar at redshift 3.42, a galaxy, a star, and a white dwarf. And on top of the spectra, we show the fluxes observed with S-PLUS in each filter. And on the right panel, I show you the near-infrared fluxes from WISE. So we have 12 points there, which matches very well with the spectra, 14 if we consider the first 2 WISE bands. And the question is, how well can we classify quasar candidates with a low resolution spectra? And moreover, do the S-PLUS narrowbands play an important role in this classification? Compared, by the way, with analysis with only 5 broadbands. And what about WISE magnitudes, for instance? So these are the questions that I'm trying to answer with this analysis. So the first data release is publicly available through this website with photometric data for about 3 million sources in the striped 2 region. This is not the data set that I used to for the analysis that I'm going to show next, actually. And the reason is because we actually used an internal data release. And the reason is that this internal data release have an improvement in the calibration, but we used the same area, the same striped 2 area for this analysis. And this internal data release will be part of the future DR2 that will have observations for about 1,000 square degrees. And this DR2 will be available in March 2021. Okay. Yeah, so let me go through the classification flow. So basically, I will explain how was our strategy and some of the results. So first of all, we retrieved spectroscopic confirmed quasars, stars, and galaxies that we got from slow-on data sets within 1 arcsecond radius. We also cross-matched with all-wise catalog within 2 arcseconds. And then these are the totals after we applied some selection criteria to get rid of spurious sources. And I also show on this plot distribution of R magnitudes and spectroscopic redshift. So for these histograms on the side, I show you the distribution for all the objects in field curves, and just for the objects that have a wise counterpart that I show you in dashed lines. And for a first look of the data, we have done some color diagrams, and this is a first attempt of doing classification. So we found these 2 diagrams that seems to separate well, at least the stars and quasars, which was the kind of confusion that we were most concerned about, because we could use a star galaxy classification before doing a star quasar separation. So here you can see simulated stars in the rainbow colors in the quasar template being redshift. And besides these models, we have the observations. So these brown points are the observed quasars that this color scales with the spectroscopic redshift. And the blue contour is the observed stars, and the orange contour are the observed galaxies. Well, so these diagrams seems to work well, at least up to magnitude 19. But here we have some caveats that we need to have detection for all these filters, including WISE. And we are also restricted to observations with signal to noise higher than 3, which was one of the conditions for making this plot. And it seems that we have more confusion for magnitudes above 19. So here comes the motivation for using a machine learning approach in order to increase the number of quasar candidates in the catalog. So for instance, we try to build a model that is robust against missing bands, and also a model that does not have to rely on wise magnitudes. Because for instance, for DR1, we would lose half of the sources if we are only able to classify sources with wise counterpart. So, okay, next step would be dividing our sample or spectroscopic sample into training and a testing set. And then we run a cross-validation on the training set. So this process here of cross-validation is for selecting the best model. So in terms of algorithm, feature space, and so on. And the models that we compared in the process are so models using different algorithms like support vector machines and random forest. And for this presentation now, it will only show you results from the random forest because it gave the best performances than SVM. And we also compare some feature spaces in order to check the importance of the 7 narrow bands and the wise bands. So these I show you in the results. So here in this table, I show you the performance of each model in terms of purity, completeness, and F-score. And F-score here is the harmonic mean of both purity and completeness. So basically, if we want both purity and completeness to be good, it can be translated in terms of having a good F-score. And the macro average F-score, that is the mean of the F-scores. So it gives an overall performance, let's say. So for a better view, I highlight here the best performances for each class. But we have to pay attention to the error bars because they can be statistically the same with another model. But in any case, if we see the macro average F-score, it seems that the model with 12 S-plus bands is leading to the best performance compared to the models that uses only the 5 broad bands, which is a good thing. So the narrow bands are helping somehow. In the end, these two models have similar performances within the error bars. But let's remember that WISE adds the problem that we lose many objects. So if we have two models with similar performances, we would choose the one that could be applied to more objects, of course. So in this case, we would choose the model with that includes the 12 S-plus bands. But if we now see the classification metrics for quasars specifically, we would see that there is no much improvements. It actually seems that all models leads to a similar performance, at least in terms of F-score. So yeah, through this analysis, we would choose the model that uses the 12 S-plus bands. And then we go further, and still in the context of cross-validation, we also check the usefulness of some morphological features. I won't show the results here, but it helps. So we included 4 morphological features as well in the classification. And then we finally get the final performance of our model by applying to our testing set. So this is a blind test process to get a more realistic and less optimistic performance of our model that I show here. So we end up with a model that the expected performance is 93.48 purity and 97.87 completeness for quasars, and an overall performance of above 97%. And we can also estimate the feature importances from the random forest model. So here we see that the H alpha filter is the most important for the classification, which is very interesting. Shows clearly how this narrow band specifically is helping for the classification. And just to mention, we are also working with photo Z determinations, also using machine learning. At this point, we reached a precision of 6%, and it goes down to more or less 2% in between redshift 2 and 3. But I'm sorry I'm not giving much details about this work because this is still our work in progress. We also have other students working with that. And also I wouldn't have enough time to talk with details about this work. But yeah, so I'll leave you with the summary. And I would like to say that our quasar candidates catalog will be publicly available with our paper that right now is under the first revision. And about future work, we would like to extend the analysis in order to classify quasars at higher redshift, because right now we are limited to the population of quasars in Sloan. And there's not many high redshift quasars there. So the classification model that we built is not ideal for these high redshift quasars. So what I'm doing is some modifications in the model for that specifically to find high redshift quasars. And I have some preliminary results that seems very good, but it's very preliminary, so I did not show here. And of course, we will try to refine still our photo Z determination, looking for a better precision, so that you will have a quasar candidates catalog with already a photo Z for them. And that's it for my talk. Thank you very much. Yes, I'm open for questions now.
Thank you very much, Lilianne. Everyone can give you a round of applause.
Okay. Well.
So I'll start with the first question. So in theory, up to what redshift can the S-plus survey detect quasars?
So I don't have the exact number right now in my head, but it's we could detect quasars at more or less redshift 5, and so because we would detect the Lyman alpha in the last red filter.
Another question. So from the testing you've done, does the completeness and purity vary a lot with redshift across the SDSS range?
Oh, that's a great question. I didn't take a look at it. I'm going to do that. That's a great question. Thanks.
And from the Slack, JT Schindler asks, Can you briefly elaborate on the size of your training sets, quasars, galaxies, stars, and where you get their identifications from?
Okay. Can I share really quickly again? So, just a second. So about the training sets and testing sets, so I divided this sample here that I have in a stratified way, so I keep the ratios the same. So I use 75% as training and 25% as testing set. Okay. And just I think this figure also helps to see the distribution of my training set and also my testing set per class. And the identification I got from this lower data set. So I used DR16 for stars and galaxies and DR14Q for quasars.
That sounds very sensible. Yeah. Thank you again.
Thank you.